This video is our first video for the Extra Topics chapter. These are topics that were not part of Calculus AP, but things you'll want to know for university. They are literally the icing on the cake. If the cake was the course, this is the extra stuff on top. And we're going to start today by looking at some things called partial fractions. Not part of our course, but something we're going to take a look at right now. These are a neat method for finding antiderivatives of what are called rational functions, but basically those are just fractions of algebra. So if you ever see a big fraction of algebra that you're trying to do an antiderivative of, this could be a great technique to do it. In order to accomplish this technique of partial fractions, we have to lean on two skills that we already have. One is integrating 1 over x. It's the only power that you don't do by reversing the power rule. It's the one that turns into ln x. Well, actually, ln x with some absolute value bars, just for safety. Right, so we'll try to remember to put those on all the time. And we can even do that integration on things that look very similar to 1 over x. Like this one here, I'm not really worried about the 2. The 2 is pretty harmless, it's just a constant. So this is an integral of 1 over x minus 1 dx. Technically not 1 over x, but it behaves like that. That x minus 1, we could do a substitution rule on it, and we would find that, yeah, indeed, you get the same deal. This would be the 2 hanging around, and then the ln of x minus 1 with some absolute value bars plus c. If you were to imagine taking a derivative of that, the x minus 1 would go to the denominator. You would multiply by the derivative of that x minus 1, but that's just a 1, so everything is totally fine. This one's even nicer, doesn't have that 2 there. This one behaves like a 1 over x, and when we integrate, we're going to get the ln of x plus 2 plus a c. And again, we'll try to remember to put those absolute value bars on whenever we can. So that's one skill that we're going to lean on. The other one is just working with fractions of algebra and how you find common denominators when you're adding or subtracting them together. So here, the common denominator would actually be the pair of factors. You would have an x minus 1, and you would have an x plus 2. And you would need to bring both of these fractions up to that common denominator. The first fraction is missing the x plus 2, so that 2 will get struck by an x plus 2. And then the next fraction, let's put that right here, it's missing the x minus 1. So the 1 that's there would get a little kick with an x minus 1. And what we know from working with fractions, even as early as middle school, is that when you're adding or subtracting, we're going to leave those denominators. So we'll just leave that as x minus 1, x plus 2. But then we would actually go in here, do the subtraction with the numerators, and then tidy it up, simplify it as much as we can, and here you would get x plus 5. Now we're going to take those two ideas, those two previous skills, and blend them together. What if you had an integral that looked like this? If you could factor the bottom and say, hey, hang on, this could be written as x plus 5 in the top, and then the bottom factors, x minus 1, x plus 2. Okay, so it's the exact fraction we just created. If you could see it look like that, then if there was a way, and I'm going to show you that there is, if there was a way that you could then decompose that and say, wait, that fraction of algebra is actually these two fractions put together. These separate fractions would actually be easier to do antiderivatives with. Okay, and we've already done those up at the top of the page. And so the answer to this question would actually just be 2 times the ln of x minus 1 minus the ln of x plus 2. We'll throw on a c for good luck, maybe some absolute value bars just to be safe. And there you go. That would be a neat way to actually do this antiderivative. I should point out there's one limitation to doing this partial fractions method. You're going to see that it only really works if these fractions that we work with are what we call proper fractions of algebra. So let's talk about proper and improper fractions. In middle school, we would have said a fraction like 3/4 is a proper fraction because that 3 is less than the 4. But a fraction that looks like 4/3, that one would be improper, because now the numerator is bigger than the denominator. Well, the same issue shows up with fractions of algebra, but we don't look at the numerical value, we look at their degrees. So if you had this fraction that we were just looking at, which was x plus 5, sitting on top of x squared plus x minus 2, if we check out the degree of each the numerator and the denominator, the degree of the numerator is equal to 1, and the degree of that denominator is equal to 2. And since the 1 is less than the 2, this is a nice proper fraction, and everything's going to work really, really well. Okay, well, let's go and try this out. We'll go through a few examples here and see if we can see how this game of partial fractions actually works. So here's our first one. It does look pretty messy, and you might be thinking, wait, we've done questions like this. We've done them with substitution. Well, that only works if you call the bottom like a blob, U or B, whatever letter you like, and then the top ends up being the derivative of the bottom. That's not going to happen here. So it's probably worth pointing out that substitution does not work here. And that was kind of our one method for doing antiderivatives, and it's off the table. So we'll try partial fractions. We're going to see if we can split that messy fraction of algebra up into some simpler ones. And here you can. You'd start off by factoring the denominator and seeing what those factors are. Of course, pulling out that common factor of the x first. And one of the things you'll notice, okay, this is one thing to be looking for, and it's happening here, so let's point this out. Got good news for you. Looking at these factors that we've got in the denominator, the x, the 2x minus 1, and the x plus 2, this is the best case situation because you have what we call distinct, meaning they're all different, linear, meaning none of them are squared, factors. That's the best case situation. All three of these factors that are there, they're all different looking, and none of them are squares. Our challenge now is going to be to see if we can find this decomposition where we can break it up into three simple fractions. Something on top of the x, something on top of the 2x minus 1, and something on top of the x plus 2. And when I talk about these somethings that I've got there just as a, b, and c, good news, these a, b, and c deals, they are just numbers. There will be no algebra up here, right? So this a, b, and c quest that we're on to try to find those values are indeed just numbers. Okay, so we really just need to find those numbers. That's going to be the big deal of the day, finding the a, b, and c values. I would suggest you try taking that equation that we have there, has a left and a right side, and let's multiply by that least common denominator. That will make it a lot more manageable, and when we do that, we're going to end up with an x squared plus a 2x minus a 1 on the left. That's all there will be. Then looking at those fractions, that first one where you have that a, when you multiply that fraction by the least common denominator, the x will reduce, but not the next two factors. You will get a little kick with a 2x minus 1 and a kick with an x plus 2. Okay, there's more. The b fraction. For the b fraction, you'll have a little bit of reducing with the 2x minus 1, but not with the x, and not with the x plus 2. And likewise, the last fraction, one with the c, the x plus 2 will reduce, but not the x, and not the 2x minus 1. Okay, there's only one trio of values that will actually work here. And the way you find them, well, there's a few methods, but here's kind of the classic way of finding them. We're going to do what we call comparing terms. So on the left, I know I just wrote this as x squared, but I'm going to call this a little more explicitly here, 1x squared plus a 2x minus a 1. Now, on the right-hand side, I'm going to start to kind of FOIL it all out, so to speak, right? I'm going to have that a, and it's going to get multiplied by a number of things. There will be, looking at those two binomials, there will be a 2x squared. So there'll be an x squared term multiplied by an a. There's more, though. There's also going to be a 3x and minus 2. So that a will have a chance to create an x squared term and an x term and just a plain old linear term as well. Just our constant term, I should say. The b term, okay, what's the b going to end up getting multiplied by? Well, doing a little foiling here, we're going to have x squared plus 2x. And then the c term. All right, that c is going to get multiplied by 2x squared minus an x. Okay, now we're going to regroup these things a little bit. We're going to look for all the times where x squareds might show up on the right? So there could be an x squared when this term hits the a, or when that term hits the b, or when that term hits the c. And so I'm just going to rewrite this right-hand side. I'm going to say, hey, how about we write it like this? What are all the different ways that you can get x squareds? Well, there will actually be, looking at the opportunities there, a 2a times x squared, but let's keep going. There'll be a b times x squared, and there'll be a 2c times the x squared. So all of those things get multiplied by x squared. Now the x's, what are all the different ways that you can have x's show up in this story? Well, the a hits the 3x, so there's like a 3a x. There's also a 2b x and minus c times the x. So all of those create x terms. And now the constant term. Well, that actually only shows up where the a hits the -2. So you would have plus a times -2. Well, actually, let's write this. Let's write that a little bit differently here. We'll be consistent. But we write this as -2a times 1, like that. So now we're just going to compare terms. This 2a plus b plus 2c, that has to be just like that one. Another one we can compare, this right here, that has to be like the 2. And then the last one, that has to be just like this -1. So we can actually create 3 equations for these 3 unknowns. And if we're going to solve for 3 unknowns, we do actually need 3 equations. So here's one of the equations. It would be 2a plus b plus 2c has to equal 1. Here's another equation. 3a plus 2b minus c has to equal 2. And one more equation, -2a is equal to -1. Now, I'm going to show you a couple of techniques for finding the solution to this system of equations. But we have seen this in Math 10 and Math 11. It is doable. It's sometimes a lot of work, but it is doable, and you can solve and find out what those values are, unless it's some unusual system that's underdetermined. This one's fine. And we end up with the a being 1/2, the b ends up being 1/5, and the c ends up being -1/10. And so we can now rewrite this story and then find the answer. And just to point one thing out here, just to offer some clarity, like this right there, if it's a little more clear in your notes to think of it this way, this is like plus an integral with a -1/10 on top, and then the x plus 2 as the denominator. That's kind of what's going on there. We're finding the little numerators, right? These things right here, the numerators for each of those fractions. I just chose to put that 1/10 as a fraction out front. Now, trying to find the antiderivative, pretty darn easy. That 1/2 is just going to spectate, just going to hang around. We're integrating 1 over x. That would be a ln x with some absolute value bars. The next one, technically this would be a substitution rule, but we can probably just do this in our head here. We're going to have a 1/5 hanging around, and then I'm suspecting it's going to be something like ln of 2x minus 1. Put some absolute value bars on it. That works pretty well, but if I took a derivative, a 2 would party crash us here, because of the chain rule. So we'll put a little bodyguard in to deal with that 2 when it shows up trying to crash the party. So you need a 1/10 there. And then the last one here, we'll have minus a 1/10, and then the ln of x plus 2, plus a c. So once we've got those values for a, b, and c, it's actually not too bad to try to figure out what that antiderivative is going to be. Let's look at a couple of different ways of finding values for a, b, and c. Let's go back to that point where after we had multiplied by the least common denominator, it's about 1/3 the way down the previous page, we had this line right here. One way that people like to see if they can quickly find these values for a, b, and c, they do a little substitution because they know that these values for a, b, and c should create an equation that's true no matter what the value for x is. So they try out three very interesting values. And here you can see I'm going to try substituting in 0, 1/2, and the last one is -2. So what is it that's so special about those numbers? Well, looking back at the original story, in the original question, those were the non-permissible values for that particular fraction. And so by now, once I've cleaned up this non-permissible problem by multiplying by the least common denominator to create this expression I have here, this equation I have here, I can now try to do this evaluation where I stick values in for x just to see what kind of story I get. And I get very nice clean stories when I do this. So I'm going to substitute x equals 0 in everywhere I see an x, not only on that side, but also on this side, all over the place. I'm going to be putting in x is equal to 0 here too. And here's what I find. This equation, which is supposed to work for any value of x, would turn into this. I would have -1 on the left. Okay, that's pretty clean. Now, here's where it gets really nice. When I start to put in x equals 0 over on that right-hand side, well, I'd have the a getting multiplied by a -1 and a 2. But then when I check out this term, when I try to put x equals 0 in to those x's right there, it destroys everything. So I get +0, +0. That is a very nice equation to solve because it only has a's. There are no b's and no c's messing this up. And so I can pretty quickly see that, oh yeah, the a needs to be 1/2. Okay, I've got 1/3 of this story finished. Then I try going back to that equation at the top of the page and trying in x equals 1/2. Yeah, okay, it's a little bit busy trying to put 1/2 in for x, but it's not the end of the world. And when you do, you'll find that that left-hand side turns into 1/4. And then moving our way along, now when you put in x equals 1/2, the 2x minus 1 creates a 0. So the first story with the a goes away. But then the part with the b, that persists, that hangs around. You're going to have a b now multiplied by, I'm just going to put 1/2 in for x. So I'd have a 1/2 because there's an x right here. And then x plus 2. Okay, 1/2 plus 2. Okay, 5/2. And then 0 for that c term. And so the only letter that persists is the b. And so I don't have to try to solve, multiple variables at once. I can just go, oh yeah, let's solve for b. And I find that b is 1/5. And likewise, if we go with that last value of -2, then we can, by substituting in -2, we can get to -1 is equal to 0. There are no a's. 0, no b's. And then the term that persists is the c term. So you'd have a c, and it would get multiplied by, in this particular case, when you put in -2, you'd have a -2 and a -5. And so for that story there, it's pretty nice. I can solve it, and I can see that in this case, the c needs to be -1/10. So that's one method, where you take that story where after you've multiplied by the least common denominator, when it's starting to clean up and doesn't look fractional anymore, you start substituting in values for x, and those specific ones, those non-permissible values, right? That's what we were putting in right here. Those particular values for, oops, not the right pen I was looking for. Let's try that again. Those particular values for x, they create very nice equations. Technically, you could put any value for x in, but then you won't have that deal where everything goes away except one letter. So by going with those non-permissible values, That actually creates nice little situations that are easy to solve. There is another method. It's called the asymptote method. Actually, I'm not even going to show you that. To be honest, it's actually just a slight variant, a slight takeoff on what I've just shown you. So instead of that, let's skip this and let's look at a different way of doing this on your graphing calculator. I'm going to go back and grab the three equations with three unknowns that we had on the previous page. We had a story where it said 2a plus 1b plus 2c is equal to 1. That was one of the equations. Now you'll notice that I didn't just write plus b, I wrote plus 1b. I really want to see the coefficients here for this method I'm going to show you. We're going to use something called matrices. And the next equation, I have to get the order right, a's, b's, and c's. So 3a plus 2b minus 1c is equal to 2. And the last one was pretty simple. It just said negative 2a equals negative 1, but I'd have to write it like this. Negative 2a, 0 b's, 0 c's is equal to a negative 1. So there's my system, and a technique for actually solving stories like this is to use some linear algebra. And in your linear algebra class that you'll take in university, you'll realize that you're kind of wasting your time writing down the letters A, B, and C. As long as you know what order things are in, really everything is packaged into this grid of numbers. 2, 1, 2, 1. There's the first equation. I'm just looking at all of those values that I see there, and I'm not even worrying about the A's and the B's and the C's. The next story has a 3, and then it was 2 B's minus 1C was equal to 2. And the last equation was negative 2A's, no B's, no C's is equal to negative 1. And that is a nice little matrix. It's just a little grid of numbers. This particular one has 3 rows and 4 columns. And there are some neat techniques you'll see next year to use matrices to try to solve this system. And I just want to show you a fast way to do it, and you'll see all the theory for it next year. And you can use your graphing calculator to help you out. You do have to enter a matrix into your graphing calculator, and it can be done. It's designed to accept matrices. The matrix button is up here, up above 1 over x. And the first thing I have to do is enter that matrix. Then I'm going to ask my calculator to solve the system and give me a nice little picture of the answers. So first of all, entering it. Let's go second. I'll turn it on here. Second matrix. Now, I've already got a matrix in there in matrix A. It looks like it's a 2 by 2. I'm going to change that. So you might have one in your calculator already. That's no problem. I'm going to edit matrix A. That'll be the one that I'll use. So I go over to edit. I'm going to hit enter. And up at the very top, it says, I got a 2 by 2 one here. 2 rows, 2 columns, right? And you can see the numbers down below. Well, I don't want that. I want 3 rows, 4 columns. So I'm going to type in 3, enter, 4, enter. And it's now created a grid that's 3 by 4. And you might go, no, it looks 3 by 3. The other ones are just hanging just off screen. They're there. We'll see them. So now I'm going to go and enter all these values in, 12 of them. It doesn't take very long. So I would go 2, enter, 1, enter. This one now needs to be a 2, enter. There's the last one for that row. 1, enter. Now the next row, 3, enter, 2, enter, negative 1, enter, 2, enter. And the last row, negative 2, enter, 0, enter, 0, enter, and negative 1, enter. There, that matrix is now stored with those 12 numbers in there. I'm going to quit out of here, and I'm going to ask my matrix part of my graphing calculator to find something that's got a fancy name. It's called reduced row echelon form, and your graphing calculator will do that. It abbreviates it as RREF. Okay, so if you're wondering, well, what was that feature on the calculator again? We're going to look for reduced row echelon form, and then we're going to put in matrix A. It can't just be like the letter A like you may have used here, you know, the alpha A. It's got to be matrix A. So to get to this, let's go back to matrix, second matrix. I want to go over to matrix math. So we'll slide over one. It's in the list, but we have to find it. So I'm going to scroll down until I find reduced row echelon form. And you might go, oh, is that it? Well, that's just row echelon form. Let's go one more to reduced row echelon form. So I hit enter and it says, okay, I'm ready to go. Reduced row echelon form of who? Well, I wanted to do it for matrix A. Not just letter A, but matrix A. So I'm going to go grab the name matrix A also in the matrix feature here. So second matrix, there are the names. I want matrix A, so I'll just press a 1. That's a little different than just an alpha A because you can see it's got the square brackets there. And I tell it, go, and it gives me the answer. And here's how you read it. This is saying 1A, and no B's and no C's, is equal to 0.5, right? So it's giving me the answers. It's saying, hey, A is equal to 0.5. Yeah, 1/2. And the next row says, no A's, 1B, no C's is equal to 0.2. Yeah, 1/5. And the last one, no A's, no B's, 1C is equal to negative 0.1. You can do this with a system of 5 equations with 5 unknowns if you want, right? It's actually really, really nice. It saves you a lot of time once you've seen how to do that. So that can be a handy little way to solve those systems. Okay, last couple of pages. Let's just take a look at some situations where you have to put a little bit of extra work in order to get these things to go. For this one, okay. Oops, sorry, I scrolled down a little too far here. There we go. So for this example 2, we've got 3x squared minus 11, and it's sitting on top of an x squared minus 4. Minor problem with that, this is not a proper fraction. It doesn't have the degree of the top less than the bottom. So we're going to have to fix it first. Okay, fixing it requires some long division. So we learned how to do this in Math 12. I'm going to do some dividing here. I've got 3x squareds with no x's minus 11, and I want to try to divide it by x squared, no x's, minus 4. You got to get all those placeholders in there, right? The zeros. Okay, so how many times does that go in? Well, I at least want to get rid of the 3x squared, so I'm going to put a 3 here, and I would multiply 3x squared. Oh, actually this gets quite nice, plus 0 x's, and 3 times negative 4 would be a negative 12. All right, subtracting. First couple of terms go away, that's a good deal. Then I would have this negative 11 minus a negative 12, so I'd have an actual positive 1. That is the remainder that happens when you do the division. And so I can now turn this into kind of like a mixed number of algebra. I can say that, hey, your old story that you were giving me, 3x squared minus 11, sitting on top of x squared minus 4, that's the same thing as just a plain old 3, that's this here, plus the remainder, okay, so that's going to go right there, sitting on top of the denominator. I am really not concerned at all about trying to integrate that 3. That'll be really easy. But that 1 on top of x squared minus 4, that's the part we have to do the decomposition with. So yeah, we'll rewrite this integral question and say, oh, I guess that's the integral of 3 dx. Super easy. Plus this one. This one needs a little bit of work. 1 over x squared minus 4 dx. Okay, so that x squared minus 4, I would factor it and create those two factors, x minus 2 and x plus 2. And then we're going to go and look for some values. The good news, these will be just numbers that are going to be in there for A and for B. All right, what next? Next step, multiply by the least common denominator. So if we multiply by the least common denominator, well, this whole denominator goes away and we end up with just 1. That's pretty nice. Now multiplying the next part by the least common denominator, the x minus 2's would cancel, but not the x plus 2's. So you'd have an a getting a little kick with an x plus 2. And then there would be a b. It's going to get multiplied by that least common denominator as well. The x plus 2's cancel, but not the x minus 2's. Okay, that's a lot nicer to work with than the line above it. And so this allows me to create a system of two equations with two unknowns. You could say that the left-hand side is actually saying no x's, and then 1 for the constant term. Now, what about here? How many x's have we got? Well, there's an ax and a bx. So there's like a plus b x. And then what about the 1's? Well, there's like a 2a and a minus 2b. Okay, 2a minus 2b multiplied by 1. And now you'd want to have things match up. It looks like, based on what I'm seeing here, looks like a plus b has to equal 0. Okay, that's one of my equations, because it's 0x on the left. And the other equation is 2a minus 2b is equal to just a plain old 1. And so you solve that system of equations. You use matrices, combination, substitution, whatever you want. And after you've solved, you'll find that the a needs to be 1/4 and the b needs to be negative 1/4. Okay, then we're ready to go. Let's take their question and let's just rewrite it. Their question now turns into the integral of 3 dx. That happened when we fixed the improper fraction. That one's super easy. Plus the integral of, all right, let's do that a one, just at the top of the page here. The a number on top of x minus 2. Okay, so there's like a 1/4, here, I'll write it that way, on top of x minus 2 dx. And another one, the b number, negative 1/4 on top of x plus 2, that b fraction. Those are doable. Those are just going to create some logarithms. Well, not the first one. First one will just be 3x. And then here comes some logarithms. Got a 1/4 hanging around, and then a ln of x minus 2, maybe some absolute value bars, and then a negative 1/4, say subtract if you wish, the ln of x plus 2, and a c. So if it's not a proper fraction, it's not a big deal. You just have to do some division first. All right, what else goes wrong? Well, sometimes you end up with some factors that are not distinct. So this particular one here, factoring it would actually be a bit of a challenge. There's no GCF we can pull out. So you have to really work at it to try to find out how that thing's going to factor. Maybe do some guessing and checking and some synthetic division, whatever works for you. But after you factor it, okay, with a little bit of work, you find you get x minus 1, x minus 1, x plus 1. That's not the best news in the world, right? We don't have distinct linear factors. They're not all different. So I'm not super happy about the fact that that factor and that factor are the same, right? Another way to write that, you could say, hey, we're, I guess, going to be integrating 4x on top of an x. Oh, just going to stop for a sec. Looks like I lost my pen. Sorry, I had a little trouble with my pen there. Try this again. So another way to write this would be, hey, we're trying to find the integral of 4x, all sitting on top of this factor here, which is repeated. It occurs twice. And then the x plus 1 dx. So we have to be careful with these repeated factors. You might think, oh, well, they'll probably just be like something sitting on top of an x squared or an x minus 1 squared. And I almost agree with you. It turns out when this thing decomposes, it decomposes into something, let's call it a, on top of an x minus 1, and then quite possibly something else on top of x minus 1 squared. You can't get it done with just one fraction. It doesn't work. You have to have multiple opportunities here to create some terms. So you have to have an A option and a B option there, and a C. There's also the x plus 1. That's the only way this thing's going to go. And then you would probably want to multiply by the least common denominator. That's been our kind of classic trick. And so I would do that and say, all right, if I multiply by the least common denominator, I get just a 4x on the left. And now as I multiply for that A term, the x minus 1, a single x minus 1 cancels, but not the other one. So you'd have an x minus 1 also show up beside the A with the x plus 1. And then the B term, you actually get a nice double canceling of the x minus 1 squareds. So the B would only get bumped with an x plus 1. And then there's the C term. For the C term, the x plus 1 term reduces, cancels, whatever you want to call it, but both of the x minus 1s do not. So it ends up looking like that. I'm going to save you a little bit of time because it's just some algebra at this point, but you can then tidy that up and regroup it. On the left, I would say, hey, probably a better way to write this would be I have no x squareds, I have 4 x's, and I have no 1s. And then on the right, if you look at all the different times when you can get x squareds, they only come from the A and the C terms, and you end up with A plus C times x squared. That's the only way the x squared terms show up. Once here and once here. Then looking at the x terms, those can show up in the B and in the C terms. You're going to end up with B minus 2C multiplied by x. And then for the units, for the 1s, all 3 terms can create that. And you would have plus a negative A and a B and a C all multiplied by 1. And so now you start equating and you say, oh, okay, well, it looks like that has to be this 0. And also, another equation we could create looks like this has to be that 4. And one more looks like this one here. That trinomial has to equal 0. And when you solve that trio of equations, 3 equations, 3 unknowns, right, you would have A plus C. Well, actually, let's go with that. A plus C is equal to 0, which if you're going to do matrices, you'd say A plus 0 B's plus a C is equal to 0. You'd have B minus 2C is equal to 4. And you would have negative A plus B plus C is equal to 0. And when you take that system of 3 unknowns, 3 equations, and solve it, you find that A is equal to 1. I'll leave this as an exercise for you to try with your graphing calculator. B is equal to 2, and C is equal to negative 1. And so we can decompose that original fraction now into 3 separate questions. Be extra careful with this one. It's actually so easy it's hard. It's not going to be a logarithm. It doesn't have that feeling of 1 over x. It actually has a feeling more like an integral. Got a right pen here. That one has more of a feeling of an integral of x to the negative 2 dx, something in the bottom squared. So we'll do the power rule backwards for that one. So for this one, final answer would be the ln, I'm going to do that first fraction here, the ln of x minus 1. Okay, got that one done. Now this next one. I suspect it's just going to be this power rule kind of backwards. Let's just kind of work it out. Just bits and pieces here. Going to raise that negative 2 exponent by 1, so it would be a negative 1. And I'm going to need a little negative 1 bodyguard there to deal with this party crasher that's going to happen because of the chain rule. And there's also the 2. So I'm going to end up with a minus sign, that's a little bodyguard, and then the 2 just hanging around. Just check it out. Take a derivative of that and see what happens. This negative 1 comes down, reduces this negative. The 2 stays there. This lowers to a minus 2. That's exactly what we want. And then one last term, minus the ln of x plus 1 plus a c. So that's partial fractions. As you've seen in the end there, the last 2 pages, you can have complications if it's not a proper fraction or if you have repeated factors. But there are ways out, okay, for both of those situations. And so it's a neat method that actually works really nice if you have messy fractions of algebra that you want to decompose.